a video. Of course, it's a video, and it's for June the 8th. Your lecture on June the 8th. We're going to be finishing chapter 2, and we're going to get into chapter 3 uh, for June the 8th, which is Monday. Wednesday, we're going to have a test, and it's going to cover chapters 1, 2, and 3. Um, Tuesday, I'm going to send you a review sheet to get ready for the. I'll get it to you by Monday night. I'll tell you what, I'll get it by Monday night, and that way you'll have some time to study for the test, which is scheduled for um, this coming Wednesday. That would be the June the 10th. I'll send you instructions on how to take the test um, next Wednesday, and also we're going to have a lab on sedimentary rocks, which will be due on Tuesday. I'll give you more information on that as well. This is going to be a short video, but let me just finish chapter 2 here. Please don't forget, this is straight out of your textbook, that the San Andreas Fault in California is a transform plate boundary where two plates slide next to each other. The two plates being the North American plate, which is to the east of the San Andreas Fault. And I guess I could keep my face up here by clicking on this float on top. All right. And then the Pacific plate, which is to the west of the San Andreas Fault. Every time there's an earthquake, Los Angeles, which is over here, west of the San Andreas Fault, moves to the northwest, and San Francisco, which is east of the San Andreas Fault on the North American plate, moves to the southwest. So what do you think? After every earthquake, does that LA and San Francisco, do they get closer together or farther apart, do you think? Think about it for a moment. They get closer together, yeah. With every earthquake, they get closer together, since that's the way transform plate boundaries work. Um, Talking about our West Coast, I know most of y'all are probably East Coast people. You grew up east of the Mississippi River, so did I. But we have a lot of interesting things going on from a plate tectonics perspective on our West Coast. And this map here that you see in front of you on the screen shows you that in the Pacific Northwest, going all the way to northern Canada, I'm not, holy mother, okay, going from the Pacific Northwest, which is Washington, Oregon, and Northern California, and this is called Victoria Island in the British Columbia province of Canada. We've got a subduction zone, so there's a deep ocean trench right here that produces the volcanic arc we have in our Pacific Northwest, otherwise known as the Cascade Mountains. South of the subduction zone here, we have the San Andreas Fault, which is a transform plate boundary. I think that shows it quite well. Let's see what a few things I just wanted to mention. Don't forget for this next test that what causes plate tectonics to occur is convection in the mantle. And convection, let me see if I get a nice picture of it for you here. Google, okay. Let's see. I'm going to try to get you a picture of it here. Mantle convection. Oh, this is a beautiful picture. Okay. Let's see if I can get this one up for you here. So, ultimately, what drives plate tectonics It is mantle convection, and here you can see how it works. We have convection occurring in the upper mantle and the lower mantle, but the the convection in the upper mantle drives the plate movement. It causes plates to pull apart. It also causes plates to subduct. Here you can see a convection cell. As heat moves up, and then when it comes into contact with the cold ocean, it cools down, and so then you form a circulation cell, which both pulls plates apart at the mid-ocean ridges or rift valleys, or it causes plates to be pushed down into the mantle. So heat is driving plate tectonics, and the way the heat is transferred within the rocks in the earth is through a process called convection. And convection is just one of the three ways in which heat can be moved from one substance to another, but it is the cause of plate tectonics. Where do you think the heat comes from? Why is it that the deeper you go in the earth, the hotter it gets? Why do you think that is? Well, it's because of radioactive isotopes, natural radioactivity in the earth, and it's a radioactive decay within the earth that produces the heat, and the heat is moved by these convection currents, and that pulls apart plates or pushes them down or moves them next to each other in the case of a transform plate boundary. There's a few other things that are covered here towards the end of chapter 2. And another thing we need to know about is, okay, we talked about the 7 kinds of plate boundaries. We also need to learn about, scroll down here. I did this part. Wilson cycles. What in God's name are Wilson cycles? Well, what Wilson cycles are remember when Alfred Wegener talked about Pangea? Well, Pangea was a supercontinent that he postulated existed 245 million years ago. That was the first supercontinent that was discovered. It existed 245 million years ago. All the continents were connected together 245 million years ago to make one supercontinent called Pangea, and we had one ocean called the Panthalassa Ocean. Well, that wasn't the first supercontinent. Since 19 since the 1970s, when plate tectonics was first brought out to the world, we've learned that there were 3 other supercontinents in the past. Another one was called Panotia. So there was one supercontinent 600 million years ago, and this is what it looked like. Panotia, Pannotia, 600 million years ago. Then if we go even further back in the past, we find there was another supercontinent called Rodinia, Roidnia, and it existed about 1 billion years ago. If we go even further back into the past, we find that there was a continent that existed 2 billion years ago, and it was called Columbia. That's as far back in the past as we can go. So bottom line is, the Earth is working in a really interesting way, and Dr. Wilson figured it out. Well, continents come together at the suture zones or continental convergent plate boundaries, make supercontinents. They break apart along rift valleys. They move apart, then they come back together again. They break apart again. They come back together again. They break apart again. What does that tell us? Well, it tells us that 250 million years from now, the continents will collide together again. It's a cycle. Here, here are the supercontinents. Columbia existed 2 billion years ago, broke apart, came back together to form Rodinia 1 billion years ago, broke apart again, came back together again to form Panotia. Panotia breaks apart, formed, and then it comes back together to make Pangea 245 million years ago. Now let's look 250 million years into the future. According to Wilson supercycles, what happens 250 million years ago? What happens 250 million years from now? It comes together again. You see that? It's a cycle, and these are called Wilson supercycles. Last thing that's covered in the chapter is hotspots. What are hotspots? Well, the best way to show you what hotspots are is talk about Hawaii. I think, Hawaii is the 50th state in the Union. It's an interesting state. I wish I was there instead of sitting on this couch. I guess you probably wish you were there too. You could be sitting there. Imagine it. You're not stuck here because of coronavirus, and you're not self-isolating and staying 6 feet away from people. No, you're sitting on a beach, and you're drinking a margarita or a gin and tonic. Life is good. Okay, anyway. Imagine this. Here's my hand here, my arm here, right here, is a plate, oceanic plate. And it's moving, right? It's moving. But there's a hot spot in the mantle. Here it is in the picture right here, the hot spot. There's a hot spot in the mantle. It's stationary. What's going to happen as this oceanic plate moves? You're going to form a volcano here. And then you're going to form another volcano and another volcano. And so here you have a volcano, then you got another one. You can start to form a chain of volcanoes. These hotspots explain something quite interesting. Volcanoes almost always occur at plate boundaries where you have subduction. But some volcanoes are found in the middle of plates. And the reason why they're found in the middle of plates is because of these mantle hotspots. Here you can see the big island of Hawaii. There's Oahu, Honolulu's there, Maui, Molokai, and Kauai. Well, this is north, this is east, this is west. So the plates, the Pacific plate is moving which direction? If this is north, that's south, that's east, and that's west. Which way are the plates moving? To the northwest, right? But the hot spot is stationary. And that explains the ages of these rocks. Take a look at this map very carefully. If I can do this, you can do this. Kauai is, the rocks have been dated at 3.8 to 5.6 million years old. On Oahu, the rocks are 2.2 to 3.3 million years old. On Molokai, they're 1.3 to 1.8 million years old. Maui, they're about 1 million years old. Hawaii, they're the big island of Hawaii, they're 700,000 years old to brand new because you still have volcanoes occurring in Hawaii right now. Well, do you notice something going on here? How does the age of the islands change as we go from the big island of Hawaii to Kauai? They get older, and it's progressively older. There's no break. Younger to older to even older to even older to even older. The reason why you see this age relationship is because Kauai was over the hotspot between 3.8 to 5.6 million years ago. Then Oahu, then Molokai, then Maui, and now the Big Island is over the hotspot. People who study the Hawaiian Islands know that the only way you can explain the ages, the difference in ages in the Hawaiian Islands is through plate tectonics. the movement of the plate over this hotspot. And back in the 80s, when you still had people who didn't believe in plate tectonics, they would say, oh, if you guys are right, then there should be a new island forming here to the southeast of the big island. Guess what, ladies and gentlemen? It's been found, and it's called Loihi, Loihi. It's Hawaiian for born of fire. It's rising closer and closer to the ocean surface, so another island will form here, and in the distant future, another one, and another one. So hotspots, like the Hawaiian Islands, show the direction in which the plates are moving. Quite interesting. And also, if you think about it, it's also more evidence that plate tectonics works. Okay, now what I want to do next is get you started a little bit on chapter 3. Chapter 3 is about minerals. Y'all have looked at 20 different minerals. Some of you did really good and got them all right. Some of you got a few wrong. Some of you got quite a few of them wrong. But you really need to focus on the ones you didn't get right so you get them right on the quiz. Here, look at these huge mineral crystals in New Mexico. There's a man there. And so this is 30 feet tall. These are big minerals. Well, what is a rock and what is a mineral? They're not the same thing. Rocks are made up of combinations of different minerals. So the only way that you and I can study rocks is by first studying minerals. That's why we did the minerals lab before the rocks lab. A mineral has 4 characteristics. A mineral must be naturally occurring. Mother Nature made minerals, not human beings. So would a diamond made in the laboratory be a mineral? No. It has to be made by nature. The second thing is minerals grow to form crystals. So minerals are crystalline. And you all know what crystals look like. Crystals have a regular, beautiful geometry. They have points and faces. They form hexagons or cubes or dodecahedrons, 12-sided crystals. So minerals grow to form crystals, which have flat faces and which meet at points. Glass looks like this. It doesn't have flat faces, and it doesn't come to flat faces that meet at a point. So is glass a mineral? No. Minerals have flat faces that make regular geometric shapes. Minerals must be crystalline. Third thing about a mineral must have is a mineral must be solid. It can't be a liquid or a gas. So would liquid mercury be a mineral? No. In French, en français, non. In Deutsch, in German, nein. It has to be a solid. Fourth thing is a mineral must have a fixed chemical composition. What does that mean? Well, what it means is a mineral such as quartz is always made of SiO2, one silicon atom bonded to 2 oxygen atoms. It doesn't matter where you find that quartz. You can find it in Tennessee. You can find it in Manitoba, Canada. You can find it in Picardy in eastern France. You can find it in Japan. It's always SiO2. Potassium feldspar is always going to have the same chemical composition. Potassium, aluminum, silica, 3 silicon atoms, and 8 oxygen atoms. So a mineral always has the same chemical composition. All 4 of those criteria must be met in order for a mineral to be considered a mineral. If you're an English major, then make a nice English sentence to remember it. for the test. A mineral is a naturally occurring crystalline solid with a fixed chemical composition. There are more than 3,000 minerals known to science, but only about 30 of them are common. And I picked the 20 most common for you to look at in your lab. And I'm going to make this video 9, and I'll see you later in video 10.